It,
So, a warm welcome, everybody, and thanks for joining us as we continue the spring edition of our 2026 ISAR Virtuaeolian Seminar series. Andrew, Maddie, Philippe, and I, along with all the ISAR board members, are excited to continue this tradition with Gao Xin. And before I turn the microphone over to Philippe to introduce Gao Xin, I would like to introduce the structure of today's webinar. Please keep your microphone muted unless we call on you in the question and answering section, the Q&A section. But please feel free to type questions in the chat at any time during the talk. But we will wait until the end to read them aloud. During the Q&A, you can also raise your hand if you like to speak up and ask your question. The meeting is being recorded, as you have heard, and will be shared with the ISAR community because there's always some part of our community who is in bed at the time of the seminars. But please hang with us until the end, since we also have some more updates to share. We ask everyone to contribute to creating and maintaining a welcoming and respectful working environment that fosters diversity, inclusions, and belonging. And now I hand over the microphone to Philippe.
okay, thank you, JB. So, welcome, Gao Xin. So, just a few words to introduce you. So, you are a researcher at the Xin Institute of Ecology and Geography, which is a member of the Chinese Academy of Science. You got your PhD in France at the Institut de Physique du Globe in Paris, under the supervision of Clément Narteau, and you have also done a postdoctoral there 2 years after your PhD. And in 2016, you got this position at the Xin Institute of Ecology and Geography, and you've been promoted full professor in 2019. Your research focuses on Aeolian geomorphology, the physics of the sand transported by wind, and sand control engineering. And interestingly, not only you publish papers, but you have also provide technical support for sand control engineering in the Taklamakan Desert in China, and also for the construction of the Great Green Wall in Africa. So today you are going to present your work on flow deflection over Aeolian bedforms, and we are very happy to hear from you. Thank you.
Okay. That's my turn, right?
Yes.
Okay. Thank you, GB. Thank you, Philip. Thank you, everybody, to the Euler Research Scientist today. Philip said, I am Xin Gao, okay, from Xinjiang Institute of Ecology and Geography, Chinese Academic Sciences, which is a research institute located, about 3,000 kilometers away from Beijing, in the westernmost part of China. And my talk today is flow deflection or Euler bedforms. Okay. Sorry. Okay. 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 That's a brief introduction. Okay. Sorry. What's happened? I know. Okay. My research work is primarily focused on the Taklamakan Desert. Also, our group have also provided some technical support for the construction of the Great Green Wall of the Sahara Desert. Okay. Mm. So this map shows the two key study areas of my work: the Taklamakan Desert and the Sahara Desert, which exhibit distinct climate change patterns. For example, in Taklamakan Desert, we have 4 distinct seasons, but in Sahara, only 2 seasons. Sorry? In Sahara, only 2 seasons are found: rainy season and dry season, which may induce different types of Euler processes and different types of dews, although they share some common characteristics, but they still have some different properties. This map, I just going to show a brief introduction of what we did is set provision as control in China. You know, in China, in Chinese Tagalog Desert, which covers an area of, 332 30,000 square kilometers. Now we have completed the largest ecological project along its edges. The total length is 3,046 kilometers long, and the desert age locking project integrates a lot of measures. For example, vegetation-based sand deflection, engineering sand deflection with a straw checkboard, and sometimes we also use photovoltaic sand control method, so which forms a comprehensive wind blow sand hazard control system. So here are some examples. Some examples is talking about this, what we have done. So we have applied a wide range of sand control measures in the work. For example, the last figure, during the flood season, we also use the extra flood to water to irrigate some plants and trees to do the sand provision and control project in the Taklamaga Desert. This is a example because we have developed a number of practical and innovative new technologies. This is an example for terrain adapted sand provision and control measures, which can reduce the cost by 97%. All of the measures, most of them are not from scientists; they are from the local people for 10 years for the experience. They can produce very good at efficient sand control method. How this is we move to the Great Great Wall. We have also contributed the Great Great Wall initiative in Africa. We hope to share China's sand provision technologies with them to help African country combat desertification. You know that the Great Great Wall of Africa is 7,700 long and 50 kilometers wide belt spanning in the Sahara, which can benefit 232 million people. So the most important goal is to halt the southward expansion of sand across the entire Sahara. This is the most important aim of the Great Wall of Africa. So this is we and in the last 10 years we have mostly carried our work in the Mauritania, which here people that they are speaking French. It is also a country known as the Desert Republic. Everywhere is sand. So we can see this picture. It clearly shows that most of its infrastructure is basically in the desert. Houses, roads, railways, and cities themselves, all of them are in the desert. So we need to do a lot of work for the sand provision control method. So okay. Fortunately, last year I visited the eyes of the Sahara, which is a truly fantastic place. It's a world wonder. So from Nouakchott, it is 700 kilometers to the place. So I hope everybody, if you have the opportunity to go to Africa, especially in the Mauritania, you can go to this place to have a visit of the eye of the Sahara is quite a good place. Okay, it's a basic introduction of what I did in the last 10 years. So also now we move to the main talk. So apart from some applied work, I mainly focus on the fundamental research. So let's move to the topic. Flow deflection over linear due. First is simple introduction and definitions. So the question is, what is flow deflection? That's the question. So I would like to say flow deflection happens when wind is changed by the terrain or obstacles, shifting the wind speed and direction away from the main flow direction and creating the secondary patterns like vortices and flow separation. It is an important type of a secondary airflow, which covers all wind changes caused by obstacles. It is very important to the Euler processes. It can affect the Euler processes. It also have some effect on how Euler bedforms can form and evolve. Yeah. So I would like to say flow deflection refers to the changes in wind direction caused by topographic theory, which is accompanied by wind speed acceleration or deceleration and occurs across the entire deuce. For example, those slope, crest, and the lee side of deuce, but it is distinct from the flow separation, and the wind can turn without undergoing separation. So, for example, this figure is from the field simulations. We don't need the separation. We can produce the flow deflection. So what is the difference between flow deflection and the flow separation? So flow deflection and flow separation, sorry, are distinct, but often can co-occur or reduce. Deflection steers attack flow to change direction, while separation detach from flow from the surface to form vortices and recirculation. And deflection can able to occur independently on very gentle slopes. That's the main difference between flow deflection and flow separation. So why flow deflection matters? So I would like to say flow deflection is a critical process that determine sediment transport, erosion transport and deposition, shapes geomorphology and can drive dune migration and elongation. It also has some direct practical applications because it is closely linked to wind blow sand hazards. There are certain infrastructure such as roads and photovoltaic power station in desert regions. So it is very important. That's why we are studying flow deflection. So now we move to some basic method. Three methods are used. I mean, field wind tunnel. We use some CFD simulations. Okay. In this study, we adopted three research approaches to investigate flow deflection and to study the related Euler bedforms. First, first method is field observation. We use the ultrasonic anemometers and different obstacles. We also use the drone for UAV topographic surveillance. The second method is the wind tunnel experiment with scaled dune models and set tracers, also including PIV. And the third method is the CFD simulation based on the renormalized group survey KEPR model, which was used to simulate the turbulent flow because this model can produce a much more accurate result under the condition of strongly separated flow than the traditional KEPR model. That's the three methods. Here is the three methods we are using for the flow deflection study. So here is the field study. The field work was conducted on a 750-meter long shaft crest linear deuce in the Kungtang Desert, which is very close to the Taklamaga Desert, just is east of Taklamaga Desert. Actually, it is located in the Nord, which is an area dominated by the unimodal northeast winds. So the field setup includes four crest normal transects. Each set has 8 ultrasonic anemometers. It has a sampling resolution is 0.5 hertz, 0.3 meters above the surface. Also, we put a reference station 50 meters away from the linear deuce which is used to capture the undisturbed background wind conditions. Now, here is the CFD simulation. We employ the CFD simulation with a polar hexagon mosaic mesh with 0.07 meter first layer height. Also, as I said, the RNG computer model was used, and also we, we need to satisfy the atmosphere boundary layer inlet profiles with a defined computational domain to model the flow over different dunes or different obstacles. Every condition should be satisfied. Okay, this figure shows the wind tunnel uh, setup. So it has the wind tunnel has a blow type. It is a non-circulating um, wind tunnel with 1 meters times 1 meter and times 4 meter test section, which is used to conduct every all of the experiment. Of course, in the wind tunnel experiment, usually it is impossible for us to satisfy the strict Reynolds number scaling for the dynamics. So we try to meet the generally recommendation of the Reynolds number independence. Actually, you our field experiment in your wind tunnel experiment, the Reynolds number is much larger than T5, which is large enough to meet the requirements of the Reynolds number independence regime. So for our present study, the maximum height of the napkin usually we set is 12 centimeters, which is 80% of the thickness of the boundary layer is wind tunnel because the boundary layer of the wind tunnel is 50 centimeters. So we usually say the maximum height of the models, wind tunnel models is 12 meters, which is 80%. That's what we did. So three key parameters we are using to quantify the deflection. The flow differential angle is defined as the difference between the wind direction measured as the deep crest, toe slope, or somewhere, and the incident wind direction in the undisturbed flow field. That means we use the reference wind station to get the wind speed as a reference wind speed. That means this undisturbed wind flow is in the absence of the due reference. So we use three very simple parameters to define the flow diffraction. These three parameters flow allows us to quantitatively comparison across all different dunes or different obstacles. Now we are studying some results in the linear dunes, nap case, and the shadow dunes. Okay, this is a very important figure, as this figure shows that the variation in wind speed and direction through our two selected sandstorm events. During the sandstorms, we can see that the wind direction fluctuated weakly compared to more significant fluctuations during a calm period. So this, let me see here. This figure shows that the ratio of the crest parallel wind components to the average wind speed at each sampling position, exceed 90%. So which indicates that when the flow encounters the due at a small incident angle, for example, here is minus 30 or 10 degrees respectively, the flow over the linear dune is dominantly controlled by the parallel wind. But in contrast, the magnitude of the wind speed component normal to the due crest is small under such a low incident angle. So this figure also to show that the speed of effect are very clear on the slope of the linear dune, even at a very low incident angle. So generally speaking, all linear dune growth with a small incident angle, the flow deflects towards the crest. Okay. Let me see. Okay, this figure, all of the figure are from the field study. So this figure illustrates the influence of the incident angle, incident with magnitude of flow deflection along the due profiles. Here we have four profiles of the linear of the linear dune. So we can see that the flow deflection on both the stones and the lee slopes appears largely independent of incident wind magnitude. So notably, we can see that sometimes the deflection angle is negative. In these two figures is negative. In the last three figures, the deflection angle are positive. So which means we have the opposing flow directions or the two slopes of the linear dune. Okay. So here we are studying the critical flow deflection. This figure shows that while the flow or the stone slope is minimally affected by the incident wind direction, it is significantly deflected or the lee slope. We identify a critical incident angle of 40 degrees. Below this threshold, deflection angle decreases from 10 to minus 50, but as the incident angle surpasses this critical value, the deflection angle increases towards zero. So here we can see there are large error bars. Why? So we would like to say the error bar indicates that the flow direction changes massively from the due crest to the lee side. The driving force to the large error bars might be attributed to two factors. Firstly, some secondary airflow occurs, such as the separation flow around the due crest might contribute to the larger variation of wind direction at the lee side region. Secondly, wind direction during non-storm days fluctuated massively, which also contribute to the larger variation of deflection flow at the lee slope. That's the reason why we can see the very large error bars here. Now we are moved to the CFD simulations. This figure shows that the wind profiles vary with wind magnitude and direction from CFD simulations. So we can see that the wind shear velocity has little effect on the wind profile pattern. However, we see that a significant increase in flow reversal on the lee slope, with the intensity of this reversal increasing as the shear velocity increases. This reversal is attributed to the adverse pressure gradient force at the due crest, which weakens as the flow recovers downwind. So let me see the below figure. What happened? This presents the wind profile for incident angles ranges from minus to 90 degrees with a constant shear velocity of 0.4 meters per second. Although the incident wind angle has a minor effect on the wind profile at the slope, it can significantly influence the lee slope. This significant response observed on the lee slope, which is due to the reversing flow occur with separated vortices. As the incident wind angle increases, the magnitude of this flow reversal also increases. As this is very important results. I mean, so this is it is with the velocity streamline pattern around the due surface. So we can see that even when the wind incident angle is zero, the flow on both sides of the linear dune is still deflected and accelerated towards the due crest. The deflection is most obvious near the due head and the sphere along the due thread. As the incident wind angle increases, the pattern of the flow deflection and acceleration of both the stone slope and lee slope change accordingly. For example, at the 30 degree incident angle, the flow or the lee slope is initially weakly deflected along the due rotation. Then progressively deflects towards the crest normal direction after reaching a maximum at the crest, but finally shift towards the crest parallel direction or the upper lee slope. It is important to know that the flow of the lee slope can also be accelerated and deflected towards the due crest, which can result a near crest parallel flow direction along the upper lee slope. which modes drives the elongation of the linear diffs, I mean. This figure shows the effects of the incident with shear velocity or the flow direction with a 30-degree incident wind angle. So we show that the incident wind magnitude has no significant effect on the flow direction near the due surface. As the wind increases, the deflection remains unchanged. This is supported, I mean, by the previous field observations that the flow deflection patterns is highly dependent on due topography. The magnitude of deflection is decreasing for example, from here to this profile, because we can see that in the S4 profile, we have the minimum flow deflection because of its lower height and rounded shape. And for this fourth figure, you can see the effect of an incident with shear velocity or the fractional speed up ratio. It remains constant. That means it remains constant no, regardless of the magnitude of the incident with shear velocity. So, which indicates that the fractional speed up ratio is constant with the increasing with shear velocity. That's the main message. Okay, this figure is, in the CFD simulations, we input all of the topography just from the field. We use the original topography to simulate the wind flow field. So this figure shows the deflection angle near the due crest magnet, which maintains a stable value. You can see here, it's just stable value is not. It keeps a stable value along the due trade, and with the incident angle and shear velocity are kept constant. In contrast, flow deflection as upperly slope is obvious near the due height and disappears towards the due edge tip. So we suggest that the shape of the dune has a substantial impact on flow deflection, with taller and steeper dune profiles being more favorable for this flow deflection effect. Okay, after in the field, we did the continuous topographic um, measurements. So the topographic data reveals that the crest of the linear dune can shift approximately 1 meter during the set storm. Notably, the average incident angle during this set storm was around 2.725 degrees. So we suggest that the flow was nearly parallel. So it means that the flow was nearly parallel to the dune orientation. So this raises a question. What drives the dune crest migration at such a low angle? That's a basic question. So we propose that the migration of dews is attributed to the deflection flow over the dew surface, which can govern erosion and deposition process, therefore influencing the migration and the elongation of the dew. So we use the wind data from four cross-sectional dew crest to calculate the set flux of dew migration. So here we calculate the perpendicular set flux, which can drive the dew migration. We then divide this set flux by the dew height and multiply it by the corresponding time, 3.5 days. Then just from the wind data, we can calculate the migration distance, which is 1.01 meters. In terms of the dew migration magnitude, look at here, it is 0.72, 0.81, 90, or 1 meters like that, which is quite constant with calculated values. So this is a very surprising result. We would like to say nearly along crest width can still move the crest perpendicular. The deflected flow has small but persistent normal component. Okay. Sorry. What happened? Hmm? Oh, so sorry. I don't know why it's okay. 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 This is the flow deflection we have studied. So also we studied some other related bedforms for induced by the flow deflection. For example, nap case, shadow dunes. So in the field, we studied a lot of depth cases. We measured the height, the width, and the h height h and the width w. Also, we studied the aspect ratio of h of w. So all of the data we all of data we acquired. So now we can study the relationship. So this figure shows the relationship between among the width W and height H and the aspect ratio of H of W of napkins, and also the length of the sand tails in the field. Notably, we can say the length is increased almost linearly with width and height of the napkins. However, the slopes of the fitting line suggest that the lengths were not always proportional to the scale of the napkins. For example, the lengths associated with large napkins were smaller than those of the shadow dunes at the lee side of the small napkins. So all of these results are supported by the Hesper result in 1981 actually. Phenomena became increasingly dominant with W of H of napkins were larger than 6 or 2 meters. Width is 6 and height is 2. That means uh, for the width of napkins of 6 meters, for the height of napkins of 2 meters, that's are these are the two critical values for the relationship between the width and the length of the shadows. Now, okay, now the field investigation shows that the length of sun shadows were not always proportional to the size of napkins. So the underlying dynamics remains are clear. This figure shows the vortex patterns related to the size of the napkins. The size and location of the vortex core region of symmetrical reversing flow shrunk and moved towards upwind region. As the width of the napkin increased. Now this finding i- is is still constant with the findings of the history in 2000, I mean 2070, sorry. The size and position of the vortex core region of symmetrical reversing flow was enlarged and moved to the downwind region, and the height of the depth increased. For example, the vortex core region rotated on both sides of the lee slopes of a napkin, where the height is 0.3 meters, but they can gradually move to the wake region, with height of napkin was about, I mean, 0.5 meters. So compare with the left figures and the right figures, we can see that regardless of the age of the winds and age of the napkins, the size of the wake region of the napkins with low H of W was very small, and the vortex core regions always rotated to the lee slope of the napkins. That's the basic message we would like to say. Mm. Here is we have some we in the field we did some field experiment. Let me see. Okay. The field experiment was conducted to investigate the shadow dune development. Gravel and sand were used to build these three dome-like mounds of equal size, 1.5 meters in height and 5.3 meters in diameter, in a shadow dune field, or April of 2020. We did this experiment. After 1 year and a half, no sand tail or sand shadow were found. That means only for the gravels and the sands, we cannot find a sand shadow behind of this obstacle. So we guess that the smooth surface of the mountains may not be conducive to the development of sand shadows. So therefore, we constructed a nylon face with a height of 20 centimeters on the surface of the of the airflow. Okay, when we finish this experiment after 1 year, we can clearly see the cell shadows here. So it implies that the nylon face roughly functioned as a plot for the napkin-like mounts. So it enhanced the roughness of the dew surface and can capture the cell tension particles. So it can promote the sand tail formation. Of course, for the development in this field, we can see a lot of the cell shadows. So another effect, the spatial arrangement of obstacles, which also plays a important role a rule of the formation and the erosion of the irregular bedforms. So this figure shows that the small spacing distance, the spacing distance between napkins can also contribute to the flow converging and potential deposition zone formation. So flow in the lee side of the napkins convert towards the center line and merges with the potential deposition zone. Where, for example, um, the distance is half of the diameter of the obstacles. This 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 sand may accumulate it in this deposition zone. So here the deposition zone we call it a secondary deposition zone, which can gradually vanish as the distance between the obstacles increases. For example, with distance is equal to the diameter of the obstacle, the second deposition zone cannot be observed between napkins, although the wake flow interaction remains strong. So here we only observe two independent potential deposition zone. Also, this right figure shows uh, tandem aligned napkins. So also the distance still plays an important role of a bit like shadow due elongation. So the width shadows can merge into a dependent one with this distance is less than LRT. Here, what is LRT mean? LRT is here. You see here, LRT is a horizontal distance from napkin top to the position, where the width velocity is equal to set transport velocity. Okay, so is here. I would like to say the spatial arrangement of the obstacle is a key factor which governs secondary flow structure and erosion deposition pattern around napkins. So we identified four flow patterns which are theoretically classified: single vortex, gap enveloped flow, and merged vortex flow, and independent flow, each corresponding to the unique sand deposition characteristics. Of course, the lateral interaction range between adjacent obstacle is we found that it's approximately 1.5 to 2 times for the obstacle base diameter. But while the critical longitudinal interaction distance is defined by the length of the upwind obstacle, the wake recovery length. This is four. So basically, the message is that we identified four flow wake patterns depending on the distance in longitudinal direction or in the horizontal direction or in the vertical directions. Sorry. So now we have other obstacle related bedforms. First is echo dews. Echo dunes usually occur upwind. It is a very simple introduction. For example, for me, echo dunes usually occur upwind of side of cliff, steep slope, and scarp, or sometimes upwind of base-alike obstacles where a reversing vortex forms is a separation flow region. This is an echo dunes. Here is some climbing dunes. So compared with the current conditions of the echo dunes, climbing dunes always occur frequently or solid obstacles, especially on the windward slope of mountains with a lower angle of the windward slope. So in brief, the key controlling factors of flow deflection are the incident wind angle, which is the most sensitive one. Second factor is the due obstacle geometry, spatial arrangement, and the process. Sometimes porosity also plays a critical role, which together determines the wind sand interaction and sand control effectiveness of the sand dune formation. So no universal critical angle of flow deflection exists. As the threshold changes with the topographic conditions and is subsequently controlled by the topographic characteristics. For linear dunes, especially, for example, the maximum observed flow deflection ranges from approximately 10 to 22 degrees. So now we move to the last part of my presentation. In desert regions, infrastructure such as buildings, sand control fences, and roads, all of this can induce distinct Euler processes. For example, horseshoe vortices can cause erosion around building foundations, while separation vortices can lead to sand accumulation near fences and roads. So the shape and orientation of the infrastructure are very important factors that can determine the severity of these wind-blown sand hazards. Here is some examples I would like to show. First is the erosion cost hazard, which are commonly observed around the base of facilities, which they are built on sand surfaces. The reversing flow and horseshoe vortices near obstacles are the driving forces of erosion and sand or other sand surfaces. Another type is the sand accumulation hazard driven by the reversing separation at hostile vortices, which is very common to human structure in arid environment. For example, this figure, this is hostile controlled echo dunes around a building in the desert. This figure is from the center of the Taklamakan Desert. So now we do some summarize. In summary, I mean, the flow deflection is a universal phenomenon across different irregular bedforms. Here, the topography, not with speed, plays a quite important role in the deflection angle, which can drive dune migration and elongation, which subsequently result in the site-specific critical angles. The same physical principles of the flow deflection can also be applied both on wind blow sand hazard control and ecological restoration in dry lands. Okay, here are some reference reference for the current presentation of the flow deflection, which can provide the theoretical and methodological support for this work. Okay, that is my presentation. Thank you, everybody. Thank you, everybody. Thank you
Yeah,
so much.
谢谢. Thank you.
Wonderful. Thank you so much. Looks like we already
Sorry.
And others, please feel free to keep typing your questions in the chat. We'll read through them. Or if you would like to ask aloud, just let us know and you can unmute. We would love that as well. Philippe, do you want to read the first question?
The first question from Yang. Grader Xin, are the intensities or effect of deflection and separation in a trade-off relationship? That is to say, one increases as the other decreases. Does this relationship hold for most different types of dunes?
I see the question from the Zoom. Are the intensity of the deflection and separation in trade-off relationship are one increase or the other decrease? Does this relationship hold for most difficult type of dunes? Let me understand this question. I didn't totally understand this question.
Maybe Yang, you can switch on your mic and ask
Yeah.
it.
Yeah, can you hear me? Hi, Philip.
Yeah, I can hear you. I can hear you. Yeah.
Hello, Yang.
Yeah, hello, hi. Yeah, great job, great work, and yeah, I'm not sure. I'm not following your presentation in the middle.
Okay.
Because you talked about the deflection and also separation, right?
Yeah.
Do they have how to say it, reverse effects?
Oh,
I
I
mean,
understand. I understand. You mean
Are they anti-correlated or something? When one increases, the other decreases, or vice versa, or something. This is what you are saying,
yeah,
right?
reverse effects. Yeah.
I mean, the flow deflection and flow separation, all of this, for example, these two types of the flow, both are the secondary. So now only talking about one flow is flow deflection. Sometimes for some, for example, sharp and high obstacles, flow deflection and flow separation both can co-occur. But for the smooth and for the smooth surface of the obstacles, I mean sometimes only fluid depression can be observed. The fluid depression can be observed without separation. I mean separation not always occur. For example, if you have a steep lee slope, we can see the separation, but we can also see the deflection. But I mean the fluid deflection can occur independently without separation. It depends on the incident with angle and the geometry of the obstacles. That's
Okay,
it.
yeah, but when they occur together, when
Mhm.
there are both deflection and separation,
Yeah.
what are their effects? Are they
Ah,
against each other? Yeah.
I mean, let me see this question. It's not easy not easy to say because when the flow deflection occurs. For example, in the lee side of dune, the separation also occurs. That sometimes, yes, the flow difference, for example, can increase the wave speed, but the separation can decrease the wave speed. Sometimes it's against each other. It is. They are against each other. Sometimes I would like to say.
Okay, I see. So I think we can
Okay.
talk about this in detail off the stage. Thank you. Yeah.
Yeah,
Yeah.
thank you.
Thank you.
Thank you, Yang.
We have
Okay.
a question from Barsha. Barsha, I'm happy to read it, or if you'd like to unmute as well. Either way is fine. Um, a question regarding the DEM used to create the mesh for your CFD simulations. And with Barkin dunes using satellite-derived DEM and struggling with the resolution. And so just wondering if you use satellite data or UAV data to get your DEMs to generate your mesh for your CFD.
Oh, I understand. Thank you so much. Actually, this field at the very beginning, we produce the grid by our mesh grid by ourselves, but later we import the measured DM data into the CFD simulation. So for example, in my talk, we use the real measured topographic data of the linear dunes into the CME simulation, CFD simulation to simulate the flow field. That is what we that's what we did. Yes, our data. I can share all of my data. It's okay. It's already published. I can share all of the data to you. It's no problem for you. No problem. So later I can send you an email. I can share all of the measured with data, measured topographic data to you. No problem. That's it. But it seems a little bit huge of the UAV data.
Hi, Xin. I'm Varsha. I hope you can hear me. Yeah, thank you so much. I just wanted to know the resolution of the data you used, if you wouldn't mind.
Yeah, yeah. You mean you mean the UAV data, right? Resolution, right?
Yes.
Oh, sorry. Usually approximately the resolution is 10 centimeters. It depends on the height of the
Oh, okay. It's very high resolution. Yeah.
10 centimeters. Yeah.
Yeah, no wonder mine is not working. I'm using around 50 centimeter resolution.
Okay.
Yeah,
Approximately
it's very
depends.
close.
Yeah, depends on the height of the fly you are flying. Yeah.
Yeah, the irony is I couldn't manage to get the UAV data because it was too windy when I did the field trip. So I had to rely on the satellite data, which makes it more difficult.
Okay. I understand. Okay. Okay. Thank you.
Yeah. Thank you so much.
Okay. Thank you.
Um, I have a question if there's
Yes.
not lined
Go
up in the
ahead.
chat or
Go ahead,
anything
Letty.
there. Okay, great. Thank you for this wonderful talk. My question is about the implications or the applications of the work for the ecological applications that you were discussing at the end.
Yeah.
Particularly around like sand fences or other type of engineering like infrastructure to modify morphology or sand transport. Does your work provide guidance or maybe some more insight onto like the placement of sand fences or the orientation to the wind or their height or just the construction of them, I guess? I think about this a lot in coastal environments, but I know it's very similar to the locations you're talking about here. And I'm just curious if you've dived into that, and maybe you haven't yet.
Yeah. Thank you so much. Actually, we didn't really use the theoretical uh, analyze to the real field. Actually, in China, in the Tagalog Desert, there we did a lot of great job of the ecological restoration. Sometimes they then plant trees or they build buildings. They leave a lot of corridors there. So I would like always I suggested them that no, you should not put in this way because you leave a lot of corridors. It will induce a strong wind speed. Also, I suggested them to based on the buildings. Building distance to based on the distance between two buildings or plenty of buildings. I mean, we give some suggestions for the arrangements of the buildings. For example, in the photovoltaic stations, or for example, in the petrol or oil stations, we provide some advices for them. Sometimes that they took my advices. Sometimes they didn't because they need to consider a lot of practical things to get buildings to put something. That's it. Yeah, I would like to suggest to use our theoretical knowledge to application. So usually, I have a lot of work in Taklamakan Desert. We have a lot of photovoltaic station. We have a lot of petrol stations. So we we have a lot of communication with them. So sometimes I suggest them to do that. Okay, usually sometimes they give me a small project for the designing for them for the, for example, the petrol stations, how to build the petrol stations, how to give a reasonable arrangement of the buildings of some, I mean, the infrastructure. That's it. Thank you.
Thank you.
Do we have other questions? I may have one, but it's almost time, so maybe a quick one. Yeah.
Go ahead, Philip.
So I would expect deflection to depend a bit on the vertical structure of the atmosphere, and for example, if the flow is in during the day or if the flow is in during the night. So do you measure something different on your big linear dunes for flow wind deflection during the day and flow deflection during the night?
Yeah, yes. During night and during day, for example, just as I mentioned, as I mentioned, the absolute the wind magnitude has nothing effect to almost, I mean, nothing effect on the flow deflection. But for the I mean, for the flow direction, I mean, for the during day and time, sometimes we have different flow directions. Of course, it has different effect, or it can produce different deflection angles. But there is one thing to be mentioned of the how do I say, the intermediate wind. For example, sometimes the wind is high, sometimes the wind is small. It depends on the. Sometimes wind is very high, sometimes, I mean, wind is very low. Of course, if we always use the set storm, we can derive the wind deflection angle. But sometimes, so if we combine all of the data from strong wind, calm wind, and low wind together, so we get different flow deflection, a little bit different, because the strong wind it changes a lot, not the direction but also the magnitude. But finally, we proved that the magnitude has nothing to do effect, or the nothing to do with the flow deflection, but only the wind direction. Of course, I mean, just now you say the big linear deuce, we have different, for different profiles, we have different flow direction angles, because the shape is quite different. For the rounded smooth topography, it can produce very low flow deflection, but it's for steep and taller deuce, the flow deflection is quite distinct.
Okay. Thank you very much.
Yeah.
It's probably time to stop because it's been an hour. So thank you very much, Gaoxin, for this presentation. So, dear audience, please remember to register for the next talk, which will be in May, the 13th of May, exactly in a month's time, by Jim Lee, and that's about it. So keep you informed with the ISAR newsletter. Maybe Maddie or JB, you want to add something before we close?
Yes, many thanks, Gao, for this excellent work, and yeah, also thanks for putting up the last slide, which announces the two next Virtueolian seminars, for which you can find more information on the website aeolianresearch.com. And then after these talks, it's July, when we'll have our ICAR, our meeting in Namibia, Swakopmund, this year. And if you want to know more about this, also please have a look at the website. Yeah, many thanks again,
Okay.
and thanks for all the audience for joining, and
Thank you, everyone.
looking forward to
Thank
seeing you.
for a wonderful talk.
Okay, thank you very much. Thank you, GB. Thank you, Philip. Thank you, all of the audience from the Euro research community. Thank you so much. It's my honor
Thank you.
to speak. Thank you so much.
Bye-bye.
Thank you.
Bye-bye.
Bye bye.
Bye-bye.
Bye, Yang.
Bye, Philip.
Everybody.